Make sure it records. Okay, so today we're going to be doing lab 8 with 2D frames and a shear wall. We're going to be considering the 2D frame. Excuse me, everyone. If you could please arrive on time and all that, that would help. Okay, so we're going to consider the 2D frame with the shear wall shown in figure 1. Model consists of 3 bays each, spaced at 10 feet, 3 stories each, 10 feet high. Going to consider the self-weight of the structure to be present. We're going to be using hips and feet, steel. We're going to be using beams and columns, W16 by 77, W18 by 97. And the shells that we're going to be using for our shear wall here are going to be 3/8 of an inch thick, and we're going to use a 2 foot by 2 foot mesh on the plates we're going to add in for the shear wall there. We're going to have 2 load combinations, the same 2 we usually use, and then we're going to have a 5 kip per foot dead load and a 10 kip per foot live load on each of the floors, as well as wind load point loads at each floor. So this is the structure we're going to be doing, 10 feet for each bay, 10 feet for each story, so nice and regularly spaced, distributed loads on each floor, and then this middle bay, we're going to put in a shear wall. Any questions? Okay, so let's open up SAP. Sorry? Oh, okay. So let's open up SAP and start a new model. Okay, we'll go to kips and feet, and then we're going to start with a 2D frames model here. So we'll click on 2D frames. Because it's nice and regularly spaced, we can use these top ones here. We're going to want to use a portal frame, so keep that as is. So we'll have 3 stories, 3 bays. Those will both be 10 feet each. We're going to turn off restraints, and then we're going to import our beams and columns. So we'll go to the plus button here, import new properties, go to I/wide flanges, AISC15, and then we're going down to our W16 by 77 and W18 by 97. We'll apply the W16s to the beams and the W18s to the columns. And when we're good with that, we can say okay. Okay, so we've got our frame in here. Now the next thing we need to do is start our define our area section for our shear wall here. Because we're going to use a shell element for that, we need to go and define it first. So we'll go to define, and then section properties, and then area sections. This is what we were doing 2 weeks ago, except this week, instead of making a 0 thickness wall, we're going to have a wall that has some thickness on it. So there's a couple types of elements we could make it. Let's keep it as shell. And then we're going to say add new section. Now in the top here, we're going to give the section a name. What we're going to be doing here is we're going to be adding a basically steel plate that's 3/8 inch thick in this whole bay. That type of shear wall or lateral force resisting system is called a special plate shear wall. Sometimes we usually use that in high seismic locations. So I'll just call this SPSW. Shell thin is okay, so we don't need to change that. And then the 3 things we need to change are over here. So first things first, we need to change our thickness for membrane and bending to 3/8 of an inch. So that's going to be 0.375 inches for both of those. And that should get you 0.03125 feet. And then we need to change our material here from 4,000 PSI, which is the default material for concrete, to A992 FY50, which is our 50 KSI steel. And once we're happy with that, we can say okay. Yes. 3/8 of an inch. So because our units are in feet, that works out to 0.03125. Okay, now let's say okay here, and then okay again. And now we have our area section defined. Everyone okay with that? Okay, so next thing we want to do is draw in our areas. So we're going to go over to the draw poly area on the left-hand side here. We see that the section that's selected is SPSW, so that's the plate we just defined. And what we're going to do is click on all four corners of one floor, hit enter, and now we have a red square. So that's the shell element applied right there. Now we'll do the same for the other two floors. And that is going to be our three shear wall plates added in. Okay, any question on that so far? Everyone up to pace? Okay, so next thing we want to do is we want to mesh our plates here. So right now, the model is considering these as just one big object, and kind of going a little bit behind the scenes in how the math works for finite element models like this. When we have shell and plate elements like that, there's some assumptions we make in the calculations that aren't necessarily true under all loading circumstances. So one thing we can do to increase accuracy is go and basically break them up into smaller pieces so that it can analyze it in smaller bits, and overall the behavior is much closer to what it is in reality. So what we want to do is we want to give it more pieces to analyze, and it'll give us a better result. Now this works up to a point because adding more pieces adds more computational complexity to the model, and we don't want to give it like a billion pieces because it'll take all night to run. So we like to find ourselves a nice kind of optimum middle ground here. For this lab, so it doesn't take forever, we're just going to do a 2 foot by 2 foot mesh. In reality, you'd probably want it a little finer than that, but it's fine for our purposes here. Any questions? Okay, so now that we have our 3 plates here selected, what we're going to do is we're going to kind of manually mesh these. There's other ways to do this as well, and SAP can do it in the background if you set up the correct type of meshing. But to kind of show you what we're doing, we're just going to explicitly do it. So what we're going to do is go to Edit, and then down to Edit Areas, and then Divide Areas. And then we have a few options here. Either the first one or the second one will do. Basically, what we want to either tell it the number of objects to divide it to in each direction, or the maximum size in each direction we should divide it to. And what the program will do is it'll try and break this down into a bunch of squares and triangles. So what we're going to do is we're going to select the second option here and then put in 2 feet by 2 feet. So that'll give us a 2 foot mesh in our rectangles here. Then when we have 2 foot and 2 foot in there, we say okay. And we see now instead of 3 plate elements, or shell elements rather, we now have 75 of them. So this should give us a much more accurate picture of what's going on in those steel plates, basically. Okay, any questions on the plates or anything we did with those? Okay. So the next thing we're going to do is we're going to apply our boundary conditions. If you look at our model here that we want to make, they're all fixed, and we have this kind of continuous fixity along the shear wall here. And that's one of the big jobs of the shear wall. It takes all the shear from the structure and translates it down to the foundation here. So we want it to be nice and fixed for all that shear transfer there as well. So what we're going to do is we're going to select everything on the bottom, and that will give us 8 points to be selected. And then we're going to assign joint restraints and make those all fixed. So we should have 8 fixed boundary conditions at the bottom there. Yeah. Oh, interesting. Do you have a 2 foot by 2 foot mesh here? Oh. Okay. So you should have 8 of these boundary conditions for the example here. Okay, next thing we're going to do is set up our loads. So we've gone and defined all of the geometric properties of our model here. Now we need to define our loads. So we're going to go to define, and then load patterns, and we're going to set up our live load and our wind load cases. So dead load's fine, self-weight multiplier is fine because it asks us to keep considering the self-weight here. We're going to make ourselves a live load and add that. And then we'll make ourselves a wind load and add that. And we'll set that to none and then add it. So dead 1, live 0, wind 0, none. Then we'll say OK. And then we're going to define our 2 load combinations. Do you know them by heart yet? Yeah, so these are 2 of our more prominent gravity load combinations, basically. And you'll use them a lot in steel and concrete design too. Usually 1.4 dead and then 1.2 dead plus 1.6 live. That's for gravity. We have a little bit of lateral loading in there, so we throw in the 0.5 wind and the other load case we do, which is a more lateral load case. Okay, so anyway, we've got 1.2 times the dead load. We'll have 1.6 times the live load. Then we will have 0.5 times the wind load. Then we'll add another one, which is 0.9 times the dead load. And then 1.0 times our wind load. Okay, so those are all of those defined. So the next thing we can do is we can select each of our floors so we can apply our dead loads and then our live loads. So let's select each of them like that. We should have 9 frames selected. Then what we're going to do is we're going to apply our dead load. So that's going to be 5 kips per foot. Then our live load, which will be 10 kips per foot. So we'll go to assign, frame loads, distributed, dead, global, gravity, force. That's all okay. Uniform load, that should be 5. Say okay there. And we've got our 5 kip per foot dead loads. Then we'll select all the same again. Then we'll go to assign, frame loads, distributed. Instead of dead, we'll say it's live. And then the uniform load will be 10 kips per foot. And then we say OK. And now we've got our 10 kip per foot live loads on all of our floors too. Okay, then finally, we want to add our wind loads as point loads at each floor. So we want 10, 20, and 30 kips point loads on the first, second, and third floor, respectively, all in the wind load case. So let's select our first floor. We'll go to assign, joint loads, forces. We'll change our load pattern from dead to wind. And then in force global X, we'll put 10. We'll select the second floor and do that all again. So we'll go to assign, Point loads, forces, still in wind, change that to 20. We're good there. And then same thing for the third floor. And there we are. So that's all of our loads applied. Any questions? Okay, so we're now ready to analyze. So let's run it. We're not going to run the modal case here because we've added a lot more degrees of freedom with all of these shell elements we've put in here. So that's going to make the model run much slower. And the modal takes a little while. So we're going to make sure we don't run that, because especially when we start getting bigger and bigger models, that can take a little while to run. But we need to make sure the dead load, live load, and wind load all run. Otherwise, we're not going to get our load combinations. And then we can say run now. Then we'll save it. And then it'll take a second to run. And then we have our results here. So this one's still a pretty fast analysis. We're not going too overboard with the number of elements yet. Everyone getting a dead load deformed shape that looks kind of like this? Anyone getting anything different? Okay, so let's go over the deliverables then. So first one, we want the reactions for each support with values and arrows for load combination 1. So we'll go to joints, click on load combination 1, hit OK, and we'll have lots of reactions down here. Those are pretty hard to read at this scale. So for the report, make sure you zoom in so we can read the numbers. You can use the rubber band zoom button up here, the magnifying glass with a square in it. That lets you go and select a square you want to zoom in on in the screen. It's kind of like a zoom window in AutoCAD. So we've got all of our reactions here, and these are in kips and feet. So these are all okay. Yeah, so these are all the reactions we have. Yeah, looks right. Okay. Then next, we will have the deformed shape for load combination 2. So we can go to show deformed shape, select combination 2. All that's fine. We're not going to turn on wire shadow today. I'll show you why. So I'll turn it on here. We're still zoomed in. So another trick you can use is the restore full view magnifying glass up in the bar up here. It's the magnifying glass with the kind of solid circle in it. This is like a zoom extents in AutoCAD. So you see here, we've got our deformed shape with the wire shadow in the background. When we have these meshed plates like this, it's a little hard to exactly see what's happening because there's just a lot of lines going on in here. So I'll just turn those off and it'll make it a little clearer what's going on here. So we can kind of see the behavior of what's happening in the structure here. Our shear wall is basically acting like a very, very stout column that's basically cantilevered from the ground here. So it's got that just single curvature bending like that. And all of our comparatively more slender elements here usually have that type of bicurvature around them when they're fixed to our frame like this. All right, so next let's look for the shear diagram and the moment diagram for combination 2. So we'll go to our shear diagram for combination 2. So select combination 2 up here. We'll select shear 2 there. And then we'll select show values down here. And we'll say OK. As we can see, we have our shear diagrams as such. We've got linear diagrams on these walls here, which makes sense because it's a uniform load. Or sorry, not walls, these beams here. And then we have just constant shears on our columns here. If you look at the shell elements or the shear on the beams that interact with the shell elements here, they're pretty small because the shear wall is absorbing a lot of that shear and transferring it down to the base, which is basically its job. Okay, so that's shear. Let's go and do moment. So we'll click on moment 3.3. And then we have our moment diagrams here. All of the constant diagrams now jump to linear, and all of our linear diagrams now jumped to quadratic. So here are our moments here. When you're taking your screenshots, do try and make the numbers as legible as possible. I know they're a little small in this one. Okay. Any questions on these so far? So these have all been stuff we've done before. Now the next one we haven't done so far, and this is going to be for our shear wall here. What we want to find are the von Mises stresses, or the von Mises stress diagram with the value of the max stress in the shear wall for load combination 2. So when we have one-dimensional beams, we can measure the forces in them, the moment, the bending moment, and the shear force, and then the axial force. And then those are pretty trivial to go and translate into like the bending stress or the shear stress. We have those equations from your mechanics materials class, my over I, the VQ over IB for the shear stress. Axial is just the force over area. So that's easy. But in 2D and 3D elements, we've got stresses going in a lot more different directions. So we need to account for all of these as well. And one of the ways we can do that is this guy right here, von Mises. He had a pretty clever idea where he basically goes and combines all those stresses similar to how principal stresses work. And it basically creates a single criteria based off of stresses going in all the different directions in the element. And we can compare that to our yield stress to figure out if all those different stresses are causing the material to yield. We don't really cover this in structural analysis too much because normally we're working with these 1D elements that we need shear and moment for, or those stresses for, and we don't need to get into the stresses and all the plates and stuff like that. Can look it up. It's a square root equation with like 5 or 6 terms in it. But what it does is it just takes all the stresses in the different directions, makes one number we can compare against our yield for. So it's nice in that way. It's a simplifying measure. So what we want to do is we want to look at that diagram to make sure all that material is still good, basically. So how do we do that? Well, we are going to go to display, show forces, stresses, and we're going to go down to shells. So we haven't done this one before. It's been grayed out in all the ones we've done so far because we haven't had any shell elements. So we're going to go to shells. You can also get it from this menu up here. And we've got a lot of options here. So first things first, we want the case or combo. So we're going to select combo 2. This is fine. This is fine. That's fine. That's fine. In the top right here, we are going to select shell stresses. In the output type here, we are going to select absolute maximum. And then in the component here, we are going to select SVM. So that stands for von Mises stresses. So we've got stresses in, it looks like 5 or 6 different directions here, and then some maximums and minimums. This one is kind of a cumulative of the maximums, and that's good for brittle materials. And then von Mies right here is a different combination of those that's really good for elastic materials, like steel. So we have SVM selected here, absolute maximum, shell stresses, all for combination 2. Everyone okay with that? Okay, so then we'll press OK. And we're going to get a nice picture here. So we've got a lot of things happening. We've got basically values for every single point on this 2D plane here. So it's kind of difficult to draw a normal diagram like we've been doing with shear and moment for that. It'd be like some 3D surface, that'd be pretty hard to read. So what we usually do in finite element is have these kind of chromatic plots where the color intensity describes the force or stress happening in the material here. So this is looking at the von Mies stress. So we're going to be looking at all these numbers are the stresses happening in our material here. And we see right now our units are in kips per square foot. If we want to translate that into something that we have a little more intuition for, perhaps we can select pounds inch Fahrenheit to get it in PSI. So if we look at what's going on in our material here, we can see that we have stresses in the material corresponding to the value on the scale here. And we have a maximum stress around 6 KSI. So 6 kips, our yield strength for this steel is 50 KSI. So we've got a ton of capacity left in this. Now, for shear walls here, those can easily withstand normal stresses. Especially with special plate shear walls, those are usually detailed for seismic events where we have extreme forces on our building that we really don't expect to happen more than once, or hopefully no times, but hopefully only once in a building's lifetime or less. And these extreme stresses put a ton of force on the building, and we need to dissipate a lot of energy so that the rest of the building doesn't get excited too much and collapse. So this one's an extremely good system for dissipating large amounts of energy, and that happens in seismic applications. So you'll see these in a couple places around the world, but they're mostly highly seismically active areas. There's a lot of other lateral force resisting systems that are much better suited than needing to put in a whole piece of plate steel for a whole bay. They're a little easier than that in most applications, but this is a good one because it just keeps everything in steel, and we don't have to worry about like adding in concrete modeling and stuff for this class. I just did it for the simplicity of keeping everything in steel, because composite stuff is a little harder to model. Okay, so we'd go and take a picture of this, and then we want to find the max value in here. So if we look at our scale, we've got kind of the purples and reds on the low ends and the blues at the high end. So we've got our blue down here. If we kind of zoom in, we can start looking for where we've got our max force down here. That's kind of hard to go and like pixel hunt for where the biggest number is. So what we can do is we can just look in the bottom left here. This gives us our minimum stress and our maximum stress. So for all of the von Mies stresses we have displayed here, that gives us our min and max. So we're just asking for the max in this deliverable. So write that number down basically in your lab report. Okay, any questions on the lab here? All right then. So thanks for coming to lab, and we'll see you all next week. Sure.